started with section 11.5. Okay, so 11.5 is taking everything that we've done from 11.1 through 11.3, which is counting principles, and then taking what we learned in 11.4, which is probability, and we're going to put it all together. So we're going to use counting principles to help us find probabilities of situations. So these first couple problems, I kind of scaffold things for you, and you're going to see that it's always a pattern, and I'm going to continue that pattern through every problem, okay? Because I got a total of, I believe, 9 problems that we're going to work through. All right? So in these problems, I always want you to begin with thinking about what is it that's really kind of going on here, okay? Is it a fundamental counting principle? Is it a permutation? Is it a combination? Once you know that, we can start going through figuring out all the information we need to find probability. And again, all of these are going to be kind of like theoretical probabilities because we're not running an experiment. We just want to know what's the probability of this situation happening. Okay, so first things first, problem number 1, it says Martha, Lee, Nancy, Paul, and Armando have all been invited to a dinner party. They arrive randomly, and each person arrives at a different time. So part A says, in how many ways can they arrive? Part B says, how many ways can Martha arrive first and Armando last? And then finally, we want to find the probability that Martha arrives first and Armando arrives last. So take a moment, think about this. Give it a shot if you want to. Pause the video. But the first thing you got to decide is this a permutation, combination, or fundamental counting principle? Use those same ideas that we talked about last time. All right. So if you said this was the fundamental counting principle, okay, then you're absolutely correct. This is the fundamental counting principle, okay? Reason why it is the fundamental counting principle is because if you think about it, does it matter how they arrive to the dinner? No, it doesn't matter how they arrive. All 5 of these people are coming no matter how they arrive. So that's why it can't be a permutation. Now, the reason why it can't be a combination, because if you're thinking, well, the order doesn't matter, if we ran an actual combination of this, which would be 5C, 5, because there are 5 people, 1, 2, 3, 4, 5. And if we are having all 5 of them come, I'm choosing 5 people to come. So that's why it's 5C5, 5 people total, and I'm having 5 of them come. Okay. So with that being said, if you actually went into the calculator and ran 5C5, you would end up finding that the answer to this is 1, and that doesn't make any sense. All the different ways that my guests can arrive, there's only one way for them to arrive? No, that's just weird. So that's why this is a fundamental counting principle, because this combination idea, it just doesn't make any sense. Okay? So I'm going to bring up, I almost forgot to bring up this application. I'm going to bring up our calculator. Okay? So we need to bring up the TI Smart View. There it is. So we'll have this open up real quick. So in that TI Smart View, again, if we ran that 5C5, you're going to see that. So no, I want to continue with my free trial. Hopefully all of you are using your free trial too. Be nice. Okay. So again, 5, hit math, scroll all the way over to prob, scroll down to NCR, you put that 5 in, see, it's 1. That just doesn't make any sense. Okay, so let's go back to our guy. And that's why it has to be fundamental counting principle. First off, the permutation doesn't work, order doesn't matter. And then second off, the combination doesn't work because 5C5 is 1. All right, so this is a fundamental counting principle. Here's why. So in part A, we want to know how many ways they can come. So right there, part A is all about finding that total that we were talking about. Okay, because in probability, remember probability is the event of what we want to happen, which is what part B is about, all over the total number of ways. So in here, this is a lot like that quiz question that you had when it said that there were 5 questions and each question had 4 answers, and we took 4 times 4 times 4 times 4 times 4. I think times another 4. Either way, all right? So this is all about guest 1, guest 2, guest 3, guest 4, and guest 5, and how they arrive. So I have 5 guests. So how many ways can the first guest arrive? There are 5 different ways because I have 5 different guests. Then after that, I have another guest that is going to arrive. How many different ways can that guest arrive? Well, there's 4 because the first guest has already arrived, leaving you only with 4 more. And then you get to the third guest because 2 have already arrived. There's only 3 left. And then you have 2. And then you have 1. So right there, that's why this is a fundamental counting principle, because all we're going to do is we're going to take 5 times 4 times 3 times 2 times 1. Okay? And we're going to multiply all that out and get to our answer, which will be let me grab the calculator. So here's our calculator. 5 times 4 times 3 times 2, times 2 times 1. Hit enter. 120 ways. So that right there, we have a total of 120 ways our guests can arrive. Okay? Now, part B. Part B is all about our event. Okay? So how many ways in our event, what we're talking about is Martha arriving first and Armando arriving 5th. Okay, so that's our event. Well, if we think about this, again, according to guest 1, guest 2, guest 3, guest 4, and guest 5, what has happened is we have limited the first guest. The first guest has to be Martha. The last guest has to be Armando. And then from there, we only have 3 guests that are left. All we have left are Lee, Nancy, and Paul. So, with that in mind, since the first and the last are already, set in stone, that's the only way they can happen, we just worry about the middle 3. So how many ways can the second guest arrive? Where there are only 3 of them left that we have to worry about. How many ways can the third guest arrive? Well, once that second guest arrives, there's only 2 left. Then there's only 1 left. So right there, now you can see that we're just going to apply that fundamental counting principle. We're going to take 3 times 2 times 1. And that will give us 6. So now all we have to do in part C is we want the probability of Martha being first and Armando being 5th. So all we're going to do is we're going to put the 6 over the 120. And all we got to do is reduce that. Because the 6 is on top is because that's what we want to happen. We want the Martha Armando event to be on top. And then down below is the total. And if you go to your calculator, let it do its job. Alpha y equals 6 over 120. And there's your answer. So we go back. 1 over 20. Yay! We did it. Let's do it again. Let's jump to the next problem. So here's our next problem. It says that there are 7 performers, A, B, C, D, E, F, and G. And they are to appear in a fundraiser. The order of performance is determined by random selection. Find the probability that D will perform first. B is that E will perform 6 and B will perform last. C is that they are in the order C, D, B, A, G, F, E. And then the last one is that F or G will perform first. So this one isn't quite scaffold, but it's going to use the same. It's going to be solved the same way that we do the other one. We're going to find the total first, and then we're going to work each one of these probabilities, figuring out each one of those events. So right now, what I want you to do, I want you to give this a shot and pause the video and go at it. Okay, the first thing you had to figure out was, is this a permutation, combination, or the fundamental counting principle? Okay, so if you think about this, you're talking about performers and you're talking about a show. So this is all about that permutation again, okay? And we talked about shows and radio shows and variety acts, talent shows, things like that, comedy acts being put in order. Those are permutations. So the big thing for this is all about a permutation, okay? So first things first, we got to find that total. Okay, in order to find that total, we are running 7 performers, P, and I've got to choose 7 of them. All those performers are going to perform. So that's why it's 7P7. I've got 7 performers total, and I'm choosing 7 of them. All right, so we're going to go back to our calculator, and we're going to do 7, math, scroll over, scroll down, oops, past it, and 7. And there are 5,040 different ways that we can do this show. All right, everything from here on out is all about the probability. So we're going to find these 4 probabilities and deal with their events. So A is all about what happens if D goes first. What is the probability of that? Well, if D is going first, that's kind of like what we had a couple minutes ago with the fundamental counting principle. You are solidifying that first position, and then everything after that, just falls out for each one of those acts. Once you choose an act, you don't go back and choose it again. So if we're already solidifying only one position, okay, then all that we have left is 6 acts. So this event of D going first is 6P6. And so we go into our calculator and we're going to run 6P6. So I'm going to scroll up just like what you've seen me do before. My poor daughter is screaming in the background. Here she's coming. And that's okay. There she is. And she's getting in trouble. I love my kids. So 6P6 gives us 120 different performances with D going first. So I go over here. That's 720. I think I might have said 120. 720. So now if I want the probability to this, the probability of D going first, all we're going to do, put that 720 over the 5,040. And we let it reduce down in our calculators. So if you let that reduce down in the calculator, you should end up with 1/7. And again, that kind of makes sense. You want D to go first, and you have 7 acts total, in order for D to go first. I mean, even though there's lots of ways for D to go first, it's really 1 out of 7, right? All right. So let's do the next one. And you see, I followed the same order as what I did earlier. Found the total first. I dealt with my event, and then I put the probability together. That was the same A, B, C, and D that we did a couple minutes ago. So this time in B, it says E will perform 6th, and B will perform last. So here, we've got E performing 6th, and what was it? D? B? B performing 7th. Okay. Well, again, just like what we did in A, you are solidifying 2 positions. Everybody before that, it doesn't matter how they go. So since we are solidifying 2 of these, that means we have a total of 5 acts left to deal with, and we're going to put them in arrangement of 5. So we want 5p5. All right, so go to our calculator. Let's run our 5p5. Oh, looks like it didn't grab my calculator. Let's do that again. Okay, come on now. There we go. So I'm going to scroll up, grab the 6p6. I'm just going to change it. Oops. Delete. And change it to a 5p5. 5p. It's too far. 5. And so there are 120 ways to do that. So we go back. Craziness. What you doing there, computer? There we go. There we go. So there are 120 ways to do this. Okay? So now if I want the probability of E to going 6th and B going 7th, all we got to do is put the 120 over the 5,040. Because all these guys are going to have that denominator, 5,040. Okay, that's not a decimal, that's a comma. So let's go back to our calculator. Let the calculator do some reducing for us. So alpha y equals, bring up our fraction, 120 over 5,040 equals 1 out of 42. So there's a probability. 1 out of 42. Okay? All right. So the next one says, well, what's the probability that they will have this specific order? C, D, B, A, G, F, E. Well, this one's a nice, easy one. Okay. Oops, we've already did blue. Let's change this to, let's do it in red. All right. So C, we want the probability, or we want the situation of C, D, B, A, G. I think it was F, E, F, E. Whoops. F, E. Well, how many ways can this happen? Well, you solidified every position. It has to be in this order. So how many ways can this happen? You're looking at it. There's only one way for that to happen. And it has to be C first, D second, B third, A fourth, G fifth, F sixth, E seventh. There's only one way for that to happen, and you're looking at it. So if I want the probability of this situation, the probability of C, D, B, A, G, F, E. All you're going to do is take that one, slap it over 5,040. And there's your probability. And then last but not least, we want to talk about what are the probabilities that F or, and that's important to us, and we're going to talk about ors a whole heck of a lot later, or G performing first. So we want F first or G first. So this is just like two separate things, you know. Let's figure out all the ways that F can happen, and then figure out all the ways that G can happen, and we're just going to put them together. We're going to add them together. This is not a bear problem, okay, because of the word or. That's why this is not a bear problem, okay? And plus, the bear problem is with combinations. These are permutations, okay? So all we're going to want to do is we want to figure out F going first and then G going first. And then we're just going to add that information together. Well, the cool thing is you already know what's going to happen here. You actually already have the number of times and know how many times F will go first. And you already know how many times G will go first because we did that in part A. Doesn't matter what letter I put there. You know, in A, it was D. Now down here in D, part D, we're talking about F, or we're talking about G. Doesn't matter. Both of those are 6p6. So how many ways can F happen first? 720. How many ways can G happen first? 720. How many ways is that total? Add it up. 1,440 different ways that F could go first or G could go first. So if we want the probability of this, F going first or G going first, all we're going to do is slap that 140 over 5,040. And if you go into your calculator and let it do the reducing that it can, this answer comes out to a nice 2/7. And there you go. Easy peasy, lemon squeezy. All right, let's hit the next one. We're getting there. All right, so this one is definitely a scaffold problem. So go ahead and take a look at this. It says a group consists of 4 men and 5 women. 3 people are selected to attend a conference. Part A, in how many ways can 3 people be selected from this group of 9? In part B, how many ways can 3 women be selected from the group of 5 women? And in part C, find the probability that the group will consist of all women. So go ahead and think about what is this, and then find that total, worry about our event, and then find the probability. Pause your video now. Okay, so let's start with A. A is the total, okay? That's what A is all about. All right, so first things first, before we figure out A, what is this? Well, because you are selecting people to attend a conference and everybody's the same, even if you're a man or a woman, it doesn't matter. They're all in a group, okay? This is a combination. Again, reason why, I mean, this is just like when we were talking about that softball problem when we talked about combinations, and it said that there's a team of softball players and they have to select 3 people to go fill up the water jugs. Again, it didn't matter who went to fill up the water jugs. They're all on the same team, okay? I just need 3 of you to go. So it's like you, and you. This is the same situation here. I'm selecting 3 people to go to a conference. Okay, I don't care if you're male or female. I just need 3 of you. So you, and you. That's why this is a combination. It doesn't matter the order. And no one is better than the rest in here. Okay? So all we're going to do is run combinations on this. And part A tells you exactly the combination you need to run. You have 9 people total. That's N. You are selecting 3 people. That's your R. So we're going to run 9C3. So we go to our calculator. Touched it too many times. There we go. So 9, math, scroll over, scroll down to, there we go, C3, enter. So there are 84 ways that we can select 3 people from a group of 9. Okay? Now, we move on to part B. Part B, this might feel like a bear problem because there are 2 groups, because when we did the bear problem, there was, we had male bears and female bears. But this is actually not a bear problem because if you look at part B, we're only taking from the women. Okay? So part B tells you exactly the combination you need to run. There are 5 women. There's N, and we're taking 3 of them. There's your R. So 5 C3. So we just go to our calculator and we run it. Okay. So I'm going to scroll up and scroll over 5C3. And there's only 10 ways to do that. So we got 10. Now all we do in part C is we put it all together. What is the probability of choosing all women? Well, how many ways can we choose a group of 3 women? 10. How many ways are there total for our group? 84. And I believe if you go into your calculator and reduce this down, you will get 3/10. So 10, alpha y equals 10 over 84. Oh, just kidding. 5 over 42. My bad. I was off a little bit. Okay? So we go back. That is 5 over 42. And there we go. Easy peasy. Now, from here on out, it's kind of like the previous problem that we did with the performers. They're not going to scaffold it anymore, okay? But I'm going to keep doing the same thing that I did right here. I'm going to find the total first, then I'm going to deal with my event second, and then I put it all together. If you approach these problems just like that, you'll be just fine. All right, the next 2 problems are all about the lottery. Very, very near and dear to our hearts. And so, looks like I skipped a page by accident. There we go. Here's our next problem. So the next 2 problems are all about the lottery. So this problem says a player wins the jackpot by matching all 5 numbers drawn from the white balls, 1 through 56, and matching the number on the gold mega ball, 1 through 46. What is the probability of winning the jackpot? Now, I don't know how realistic this is for ours, because I don't know what the numbers are chosen on the white balls and the actual lottery that we have going on. And then the mega ball, I don't know if they are the numbers 1 through 46. But what you do right here, this process, is the same way you can figure out your chances of winning an actual lottery, actually any kind of lottery that you want to look at, depending on the number of balls that they have and things like that. This is the same process. So let's show the second problem real quick. The second problem says a player wins a minimum award of $10,000 by correctly matching 4 numbers drawn from the white balls, 1 through 56, and matching the number of on the gold mega ball, 1 through 46. So here it says, what is the probability of winning a consolation prize? So both of these problems are the same idea. They can be the same concept. So the question is it a fundamental counting principle? Is it combination? Is it permutation? And then from there, the first thing we're going to do is find the total. Then we will deal with the event, where the event in the first problem right here is what's the probability of actually winning? And then the event in this one is what's the probability of matching 4 white and the gold ball. So we'll deal with that event. And then we find the probabilities from there. So go ahead, pause the video, and start working on this problem, which was the second one, the consolation prize problem. And then here is the first problem that we'll actually talk about, which is winning the jackpot. Go ahead, pause the video, give these a shot. All right, here we go. So the first thing we got to talk about is the total. Okay. So in order to get the total, this problem, if you think about it, again, you're drawing 5 numbers and then you're drawing a gold number. Okay. This is a lot like playing cards, where you're given 5 cards. It doesn't matter the order of the cards, as long as you have what you need. You know, like if you're looking to get a 4 of a kind, as long as you get those 4 cards, it doesn't matter when they're drawn to you. As long as you get 4 matching cards, that's a 4 of a kind, no matter when you got them in the 5 cards being dealt. It's the same situation here. Since it doesn't matter how you pick your numbers, as long as you get the 5 numbers, you win. This is a combination. So in order to find the total, we're going to run combinations. Now, this is a bear problem, because in order to win, I got to pull from the white balls and I got to pull from the gold mega balls. That's like having the males and the females. Okay? So to get our total, in order to win the white balls, we have 56 numbers we're choosing from. And we're going to choose, well, if I want to win, okay, well, actually not win. Don't worry about the winning, but I need to choose 5 of these. Okay? There are 56 numbers. You're going to choose 5. So this is for the white balls. Let's call those WB. White balls. So we go to our calculator, and this number is going to get high, guys. This is a large number. Okay? No way around it. So we got 56, math, choose 5. So you got 3,819,816. 3,819,816. That's how many ways we can choose 5 numbers from 56. Now the gold balls. Well, there's only 46 numbers, and we're choosing just 1. Okay, if you remember from anything that we've done in previous examples, if you have 46, choose 1, that's actually just going to be the total number. How many ways can you choose 1 number from 46? There's 46 ways. You just pick one of those numbers. Doesn't matter. If you go to your calculator and verify that, you'll see that that's true. So to get our total, all we're going to do is we're going to take 3,819,816 times 46. And again, this is going to be a very large number. So I grab my calculator. I'm going to scroll up, grab that number we just had, and all I got to do is multiply it by 46. And there it is. 175,711,536. 175,711,536 ways to make a lottery ticket. That's a lot. All right. So now our event is all about being the jackpot. Okay? Well, in order to be the jackpot, you got to match all 5 numbers and the gold mega ball. How many ways can we do that? There really is only one way. Because again, though, if you go in here and you think about it, I mean, if you want to match the 5 numbers, so there are 5 numbers, how many ways are there to match that? 5. 5 choose 5 is only 1. Same thing with the gold mega ball. There's only 1 gold mega ball. How many ways to match it? 1. So 1 times 1 is 1. There's only 1 way to win the jackpot. Either you have the numbers or you don't. Okay? So, in the end, if I want the probability of a jackpot, the answer is 1 over 175,711,536. That's the probability of winning the lottery. So kind of put this in perspective, giving you kind of like a percentage for this. 1 divided by 175,711,000. Sorry, 175,711,536. So that e to the negative 9 means that it is scientific notation. Okay, so if we look at this in unscientific notation, it looks like this: 0.0000000 0, 0, 5, I think there was a 9, and whatever the rest of it was. So that's the decimal version of it. If you want to think about it as a percent, it would be this. 2, 3, 4, 5, 6. That's a percent of winning the lottery. 0.0000059%. You see why it's pretty tough to win the lottery. All right. So let's talk about this case. Again, our total doesn't change. Our total is still the same total from before because our numbers are still the same. 56 numbers, 46 there. So our total is still that 175,711,536. Okay? Now, our event is this consolation prize. Okay? So our event is we want to match 4 white balls and we want to match the mega gold ball. That's our event. So again, it is, a bear problem. So let's start working on this. First things first. So we're going to match 4 white balls. Well, first thing we got to talk about is how many ways are there we can match 4 white balls. Okay? So there are 5 numbers total. And again, we want to choose 4 of them. So we want to match 4 of them. Okay? So let's get that number. And it's going to be 5 choose 4 is 5. There are 5 ways to match that. Okay? Now, we got to talk about how many ways are there to match the last ball that we get. So this right here, these are all the different ways we can match 4 balls correctly. Okay, there's 5. And then we got to talk about all the ways that we can match or not match the last one. So remember that there are 56 balls total. But remember, 5 of those numbers are going to be correct. Okay? So how many balls are not going to be the correct numbers? That's 51. So for this last ball, we have 51 numbers to choose from. And again, how many of these incorrect ones do we need? Just one of them. Because we're going to match 4, and then this is going to be the number that's off. So 51, choose 1. That's going to be 51, according to the calculator. So all we do now is take 5 times 51. And that will give you, I believe, 255. So if we want the probability of the consolation prize, which is that situation that I have described above, we're going to match 4 white balls, and we're going to match the mega gold ball. All we're going to do is put that 255 over the 175,711,536. And again, we're going to go to our calculator and let it reduce this down. So let's see what happens. So alpha y equals 255 all over 175,711,536. Ooh, notice it kicked out a decimal for us. So again, this is a very, very small number. So what happens when our calculators can't handle this? Well, this is where we got to go to my best friend, the internet now. Okay? So we're going to jump out here to the internet. And we are going to come up here. And we're going to type in. What we need is a fraction reducer. oops, not fraction. Reducer. There it goes. Pops up right there. Oh, you also see down here, it says fraction reducing calculator. So you can click on that. And I just grabbed the top one. The calculator soup is very, very good. I use it all the time. So all you do is you just come in here and you put in the numbers that you need. Okay. So I've clicked in there, backspace. So we're going to put 255 in there. And down below, we'll put in our big number of 175,711,536. Calculate. So it's working. And there's our answer. 85 over 58,570,512. Okay. So we go back. So 85 over 58 million. I got to grab that number again. Where was that screen at? There it is. Bring it up. 58,570,512. 570, 512. 570, 512. And there we go. Dunsies. All right, jumping to the next guy. All right, so this one, it says a box contains 25 transistors, 6 of which are defective. If 6 are selected at random, find the probability that A, all are defective, and B, none are defective. So go ahead, think about what this is. Is this fundamental counting principle? Is this permutation? Is this a combination? Okay. Once you know that, find the total, and then start worrying about these different events. And pause the video now. Okay. So, first things first. Let's get that total. Because this is going to be the denominator for all of our probabilities. So, in the end, we have 25 transistors. We don't care if they're good or bad. We have 25 of them. And we're going to choose 6 of them. Okay, this is definitely not a fundamental counting principle because, again, you only have one group. We're choosing transistors. Okay, sometimes they work, sometimes they don't. Now, does it matter how we choose these? No, I'm just picking 6 of them. Okay, they're not ranked in any order. I'm just, this is just like the conference problem that we had a couple seconds ago. Okay, I just need 3 people to go to a conference. I've got 9 of people to choose from. In this one, it's like I've got a group of 25 and I just need 6 of you. Okay, so this is definitely a combination. So now that we know it's a combination, we just go to our calculator and run 25C6. So 25C6. Bring up the calculator, 25, math. Go over C6. Okay. And so there are 177,100 different ways to select people to go, or to select transistors. Excuse me. Okay. Now we start dealing with each piece. So right here, part A, our event is that they are all defective. This is going to be a lot like what we just did kind of with the choosing the ball problem for the lottery that we just did with the consolation prize. Okay, we're only going to focus in on defectives here. All right. So if you focus in on nothing but the defectives, okay, that means how many defectives do I have? I have 6. And I want to choose how many of them again? 6. Okay. So because we're talking about nothing but defectives, that's what we're going to focus in on. This is just like what we were talking about with the mega ball that we had a moment ago. Okay. If I want to get 4 correct, I have 5 numbers and I want 4 correct. How many ways that can happen? We saw that it was 5. Okay. And just like when we're talking about choosing all women to go to that conference, all I did was narrow it down to the women. We didn't care about the men. Okay. We just wanted to know the women. So there were, I think there were, I can't remember. So let's just say, there were 5 women and we wanted to choose 3. Okay. So in this one, we just care about the defective. We don't care about the non-defective. So that's why it's 6. Choose 6. And if you remember me talking about this right at the beginning of this lesson, whenever you have a combination and the total number and the R are the same, the value is 1 as an answer. And again, you can go to your calculator and check it. So what's the probability of all defective? Well, that will be 1 out of 177,100. And there you go. There's part A. Part B, this time it says none are defective. So that means we're just talking about the other group. Well, if you're not defective, that means you're working. So how many transistors do I have that are working? Well, there are 25 transistors total. Oops, don't scroll down on me, silly. There are 25 transistors total. 6 are bad. So if I take 25 minus 6, that means there are 19 transistors that are not defective. And how many of these do I want to choose? 6. So we go to our handy dandy calculator. Okay, and we've got 19. Choose 6. So there are 27,132 ways that we can choose non-defectives. 27,132 ways. So what's the probability of none being defective? Well, that's the 27,132 all over that 177,100. Again, let's go to our calculator and let's let it do its job for the fractions. Okay? Alpha y equals 27,132 all over 177,100. Enter. Oh, our calculator was able to handle this one. So 969 all over 6,325. 969, 6,325. So our final answer, 969 all over 6,325. Make sure of that again. Yeah, it should be it. Let me just double check. Yep. 969 over 6,325. Perfect. And there you go. Hopefully you're starting to get the hang of this. I know this section could be a pain. Believe me, I get it. But we're going to get through this. You guys are doing great. Okay. And I chose these problems for a reason because they might show up somewhere else. Wink, wink, nudge, nudge. Homework. Test. All right. So, a city council consists of 6 Democrats and 4 Republicans. If a committee of 3 people is selected, find the probability of selecting 1 Democrat and 2 Republicans. So this guy right here, like I said, when I told you before, your book likes to get political. They love throwing these Republican Democratic problems at you. Later on, they'll start throwing in independents, and they'll also throw in another group too. So your book loves to get political with these things. So again, we're talking about forming a committee of 3 people with the city council. So think about this. Is this a fundamental counting principle? Is this a combination? Is it a permutation? Find the total, then deal with the event, which is all about 1 Democrat 2 Republicans. So go ahead, pause your video, give it a shot. So if you said that this was a combination, you are correct. Because again, you're just forming a committee. Whenever you want to form a committee, a group, do something, where it just takes people, that's a combination all the time. Because it doesn't matter. You just want people to do this. So it's like you, and you, go. Okay, hopefully you started catching on to that. And hopefully you kind of see that a lot of our problems are combinations. So weird. And also, if you've been looking at this problem, in the end, I want 1 Democrat and 2 Republicans. Hope you're thinking about this back to that bear problem, because this is a bear problem to figure out. Okay? So, let's first start with the total. Okay? So, I have this city council. How many people are on it? Well, there are 6 Democrats, 4 Republicans. So that means there are 10 people total. And we want to choose, what do we want a committee of? 3 people. So we're going to run a 10, choose 3. Let's go to our calculator, 10, math, choose 3. And there we go. So there are 120 ways that we can choose a committee of 3 from 10 people. Okay? Now let's deal with the event. We want 1 Dem, 2 Republicans. So let's talk about the Democrats first. So how many Democrats are there? There are 6. And we're going to choose 1 of them. Well, 6 choose 1. If you go into your calculator, it will give you 6. Now, if we talk about the Republicans, how many Republicans are there? There are 4. We are choosing how many? 2. 4 choose 2 gives you an answer of 6. So if I want to know how many ways can I choose 1 Democrat and 2 Republicans, that is a 6 times 6, which is 36. And so, finally, what's the probability of 1 Democrat, 2 Republicans? Well, that's 36 over 120. And this, my friends, will reduce. I believe this is the answer that I gave earlier of 3/10. So let's just make sure, though. So alpha y equals 36 over 120. Yep, 3/10. And there's your probability. Only got 2 more problems left. They're both card problems. So I put these on here because I want to keep reviewing that deck of cards that we talked about in 11.4, because you're going to see it a lot. We like the deck of cards. All right, so here it says, if you are dealt 3 cards from a shuffled deck of 52 cards, okay, it's a standard deck, find the probability that all 3 cards are picture cards. Okay, last problem, because it's just like this. Again, if you are dealt 4 cards this time from a shuffled deck of 52 cards, find the probability of getting 2 queens and 2 kings. Okay, so those are the 2 situations. Both of them are the same type of situation. That's why I'm showing you both. So go ahead, try this one. Figure out, is this a fundamental counting principle, combination, permutation first, and then find the total and deal with the event. Same on this one. Go ahead, pause the video now, give them a shot. All right, so let's run down these last 2 problems. So you're just being dealt 3 cards. Does it matter how you're dealt these 3 cards to end up with 3 pictures? No, as long as you got 3 pictures in the end, you're good to go. And the same thing over here. You're given 4 cards. Does it matter if you get 2 queens first and then 2 kings, or if I get a queen, then a king, then a queen, then a king? Didn't I still end up with 2 queens and a king? So because it doesn't matter how I'm getting my cards and when I get these cards, both of these, if you guessed combination, you guessed correctly. And the crowd goes wild. All right. So First things first, let's find the total here. So the total, how many cards do I got? 52. How many am I picking? 3. So we go to our calculator. And I type in 52. Oops. 52. Math. Too far. Choose 3. All right. 22,100. Okay. So let's jump back here. 22,100. All right. So now what's our situation? Well, we want 3 pictures. And because we are only focusing in on pictures, I don't care about any of the other cards. So how many picture cards are there in a standard deck? Again, if you go back and look at our information from the previous day, I gave you this answer. There are a total of 12 picture cards. And we're choosing how many of those? 3. So all we got to do is run 12C3. Go on our calculator. Oops. 12, math, C3. So there are 220 ways that can happen. All right. All we do now to find the probability of 3 picks, take that 220, slap it over the 22,100, and let the calculator do the reducing. So alpha y equals 220 all over 22,100. Enter. So 11 over 1,105. 11 over 1,105. There's your probability. Yay! Last problem, and we did it. Okay, this is a similar problem, although when we get to the event, if you notice, it says 2 queens and 2 kings. This is a bear problem. Okay, once we get to the event, a lot like what we just did with the Democrats and the Republicans. Okay, it's a bear problem. All right, first things first. Total. So this time, again, we have 52 cards, but this time we're choosing 4. So let's go to our calculator. Just going to run right back up here and grab the 12. I should have grabbed the 52. My bad. Change that to a 5. Come over here. Change this guy to a 4. Should have grabbed the 52, choose 3, but I didn't. So there we go. There are 270,725 ways that we can take 52 cards and choose 4. 270,000. Oh, what was that other number? 725. Whoops. Went back too far. Okay. Come on, you. There we go. 725. All right. Our event. 2 queens, 2 kings. So let's start with the queens. How many queens are in a deck? There are 4, because you have 1 for each suit. Queen of hearts, queen of diamonds, queen of spades, queen of clubs. And we're going to choose how many of those? 2. The kings will work the same way. Once we know the answer to the queen question, the king one will have the same answer. Because again, there are 4 kings. King of hearts, king of diamonds, king of spades, king of clubs, and we are choosing 2 of those. And then once we get these 2 answers, all we got to do is multiply them together. So grab our calculator. So we've got 4, math, choose 2. 6. So 6 times 6 is 36. Because this is 6, this is 6. We're going to multiply those two answers together. So there are 36 ways to have 2 queens, 2 kings. So what is the probability going to be? 36 all over 270,725. And then I yield to the calculator to let me know if this reduces. So we bring that up. 36, sorry, clear that out there. Alpha y equals, I actually cleared everything out. 36 over 275. Forgot my number. Oh, sorry, 270 all over 725. Scroll back. 270 all over 725. And it didn't like it because there's too small of a number. So we go back into our fraction reducer. We come right over here, bring up my little keypad. So 36. Come down here, get rid of these guys. 270,725. And that is the answer. It does not reduce. Oops, wrong one. So there's your final probability. Good luck, ladies and gentlemen. I know you've got this.